Good day. In the previous episode, we have solved the Schrödinger equation for the particle in the infinite potential well. We have showed that in case of confining potential, the energy spectrum of the particle is discrete. In other words, the particle can have only discrete values of only certain values of the energy. In this episode, we'll consider the non-confining potential, or the barrier potential, in other words. In classical physics, the particle cannot penetrate barrier if it have not enough energy. So, if you have some kind of a hill, the particle, if it has not enough energy, will go up and turn and stop at some point and turn in other way. So the particle will be reflected by this barrier. If it has enough energy, it will definitely go up and down, and the particle will be transmitted through this barrier. So in classical physics, the choice is binary. Either the particle will be reflected from the barrier, or the particle will go through the barrier. In quantum mechanics, the things are quite different. We'll consider the simplest case, the case of Dirac delta function barrier. What is this Dirac delta function? That's a function that equals to infinity at one point x equal 0. At any other points, it equals to 0. So, Dirac delta function is equal to 0 if x not equal to 0, and equals to infinity if x equal to 0. So, the Dirac delta function presents an infinitely high but infinitely thin barrier. The defining property of delta function is that any integral of this function, product of this function, with the product of any continuous function f, a, b, is equal to the function value at 0. This equality is valid only if the segment AB contains 0. So 0, AB. That is the defining property of the Dirac's delta function. So you can see that in that case we can divide our space into two regions. At each region, the potential energy is equal to 0. And in that regions, the Schrödinger equation will be ultimately simple. That Schrödinger equation can be solved at each region, and the solution is a simple superposition of the exponents. So, that is the solution of the Schrödinger equation in both regions. What is the physical meaning of this solution? We can act by the momentum operator on each exponent, and you'll see what we'll get. You see that each exponent is the eigenfunction of the momentum operator, and the eigenvalue of this exponent is p, the momentum of the particle. So that exponent corresponds to the particle moving from the left to the right, or having the positive momentum. This exponent corresponds to a particle having negative momentum and moving from the left to the right. The same for the second zone, second region. So, in the first region, let's consider that the incident particle is going from the left to the right. So it is represented by this exponent. So that exponent stands for incident particle. That means that exponent corresponds to the reflected particle that moves from the barrier to the minus infinity. The same for this region. This exponent stands for transmitted particle that goes from the left, going through the barrier from the left to the plus infinity. And this exponent stands for the reflected particles. But this reflection, there is no object in minus infinity to be reflected from. That is why there cannot be any reflected particle in the second region. That is why the coefficient d should be equal to 0. So, we have solutions of the Schrödinger equation in both regions. Next, what we need to do is to join them. You already know the first joining condition is that the wave function should be continuous everywhere. What is the second joining condition? The second joining condition can be found from the Schrödinger equation. We can integrate this equation in the vicinity of some point A. The first integral can be evaluated explicitly, since we have only second derivative here. The third integral can be simplified in the limit of 0 epsilon. That can be done because the wave function and the energy is considered to be finite at every point. What about the second integral? If the potential is finite too, it can be treated in the same way as the third integral, and we will have. So, in the limit of the 0 epsilon, these two terms can be neglected, and we will have the final joining condition. That condition is a just stating of the continuous not only of the wave function itself, but the first derivative too. So that is two joining condition for good finite potential. But what we have in our problem is the singular potential that is equal to infinity at some point. What will be in that case? Let's do the math. So, for delta function, this integral will be equal to the following, as we already know. And in the limit of 0 epsilon, you can see that the third term goes out in that time too, but the second term is now not 0. So we have finally such a joining condition. So that is the joining condition. We can easily solve this system of equation and get so That is the solution of joining equations. You can easily check that the sum of the squared moduli of coefficient B and C is equal to the squared moduli of coefficient A. That's a very important equation because it indicates the conservation of particle current. The coefficient A corresponds to incident particle, and we can see that it splits to two currents, the reflected one and transmitted. And that equation states that the incident current is splitted into two currents, and it indicates the conservation of the current and the particles. So we're ready to write down the solution of the Schrödinger equation. So, the solution of the Schrödinger equation in the first region is represented by the incident particle and by the reflected particle. And the solution in the second region is represented by the transmitted particle. You can see that, in contrary to the case of confining potential, in our problem, the particle can have any positive energy. Or, in other words, it have continuous spectrum. And that is usually valid for non-confining potential. Coefficients B and C and A can give us so-called transmission and reflection coefficients. So, that is the transmission and reflection coefficient. Let's analyze it. You can see that at very high omega, that is very strong potential barrier, the transmission coefficient tends to 0 and reflection coefficient tends to 1. That indicates that the very strong potential makes the barrier impenetrable. The same is valid for very large masses and very small Planck constant. Both these limits brings us to classical limit, at which no wall can be penetrated by the particle. So, and the last limit is the limit of high momentum. We can see that at infinite momentum, the transmission coefficient tends to 1 and reflection coefficient tends to 0, which indicates that very energetic particles can easily go through the barrier or go through the walls, and they do not reflect from the barrier. The another important case that cannot be considered in the framework of our problem is the case of particles that have the energy larger than the barrier height. In that case, in classical physics, the particle can go through the barrier with 100% probability. But in case of quantum mechanics, we can show that the particle will reflect even having higher energy than the barrier. So, in that episode, we have seen that unlike the classical case, the quantum particles can go through the walls or even reflect from the bombs lying way below from the particle. We have shown that in case of non-confining potential or barrier, the particle have continuous spectrum. That is, it can have any positive energy. In the next episode, we will discuss the probably most important problem in quantum mechanics, the quantum oscillator. Thank you very much.